I'm going to build two kits for audio oscillators or function generators. This one is by Rainbowkits. It's considered to be an educational block in a series they have. That's in New Ross, Indiana. It's just considered an audio oscillator EBAO-3. Cost a few dollars. Bought it on Amazon, I believe. And then there's this other nameless product that's considered to be more of a function generator kit. I figured I would build both of these and just see how they work out and maybe describe them a little bit in this video. Yeah, right up here, the Rainbowkits oscillator was in fact purchased from eBay. This is what the eBay listing looks like. It just calls it by the EBAO-3 Veenbridge Audio Sine Wave Oscillator Kit. Here's the listing, and it's not being sold by the outfit in Indiana. It's being sold by who the hell is it? CQ Radio Supply Company in El Dorado Hills, California, and it costs $16.95. And they do show the 5 pins being used in those scattered locations, and the circuit board doesn't even have the holes for the 3 pins side by side. So again, they've made a circuit board change. They haven't really updated the parts list or the description to match. What they say about here, audio oscillator, blah blah blah, produces sine wave between 5 Hz and 50 kHz. May operate over 100 kHz with increase in distortion. Output amplitude is approximately 2 volts peak to peak, which isn't correct either. Default frequency is set at 500 Hz with the component values provided with the kit, and may be adjusted by changing 2 resistors. Well, it says 2 resistors, and they say R5 plus R6 plus R9. I think R9 is the trim pod, so and or 2 capacitors to get within the range. So they do allow in this listing that you have to change parts to change the frequency. So they're not lying here. It's just the instructions would have been good to include some more of this information. There is their website and address for Rainbowkits. Sine waves are pure audio tones typically used to test audio equipment. This audio oscillator kit produces sine wave audio signals. Output amplitude is adjustable. Use this kit to learn the signal injection method of audio circuit troubleshooting, or connect 2 or 3 together to produce complex audio signals such as DTMF, dual tone multi-frequency, phone tones. Connect to the audio amplifier EBAA-1 and hear the sine wave tones. Requires plus 9 volts DC. So what we get is the decent looking printed manual. I always appreciate printed manuals with these things. And a small bag of parts. Here are all the parts that are in the bag. A single-sided fiberglass circuit board. Looks like it's good quality. Has a good silk screen on the front. And respectable size through-hole pads. No surface mount stuff here. Several, 7 quarter-watt resistors, a couple of electrolytic capacitors, a couple of red LEDs, a 5-pin pin header, 3 ceramic capacitors, and that is it. Oh, I forgot the IC socket, the IC, and 2 trim pots. I've noticed a little sloppiness in the manual, and it's inconsistently reproduced. I think it's being just printed on a color inkjet printer. It kind of has that look. It doesn't look laser printed. So there's a very brief theory of operation here on the left inside cover, and then it concludes, and then the first page, page 1, starts right in the middle of a sentence, and I'm thinking, what the heck? And then I'm looking around and I realize that they're kind of starting about here, like maybe they had a different inside cover originally, then replaced it and didn't correct this. So okay, that's a little bit careless. They describe in here that the circuit is a op-amp based Weinbridge or Veenbridge oscillator circuit. I've always called this a Weinbridge, but the way it's spelled it should be pronounced Veenbridge or Veenbridge, as in Vienna maybe, I don't know. I never looked into the source of that word. I presume it's somebody's name. But anyhow, they describe how there's both positive and negative feedback in the circuit, and that there's 2 RC pairs, and one of them forms a high pass filter, the other forms a low pass filter, and the point where a signal can oscillate and not be rejected by either the low pass or the high pass filter, then that's your center of your oscillating frequency. So they have a little bit of that. Then they have some more specific theory, which again seems to be repeating what's over here. And then they say, well, real world engineering, now we have to have variable gain control. And they have some other stuff. Considering this is supposed to be an educational kit, and as a former electronics educator myself, I think they could have done a little better job here. I'm glad they're putting out the effort, though. But it's kind of like the person who's doing it's a little bit impatient and is writing at his own level and not dumbing it down quite enough to probably the real target audience of a kit like this. Yeah, I don't think that some total newbie is going to be able to make sense of this circuit description. Although, you know, if they pour over it and experiment enough, it might sink in. Anyway, so we have a parts list, we have the full schematic, we have the parts diagram. Oddly, this manual is bound with a staple, but it's only one staple. It's like, who does that? If you're going to put in one staple, put in 2. It's just makes the whole thing feel like it's falling apart. Come on, guys. And then step-by-step assembly instructions and how to test it. Now insert the IC, so they have a bunch of pre-IC installation tests. Attention to kit builders. Cost to repair your kit, $15. I think that costs more than the kit. I don't remember what I paid, but well, at least they have a repair service. An awful lot of companies that produce kits these days, you know, you're on your own, so good for them. All the discrete resistors are on the board, and the IC socket. I put that on first, even though the instructions don't mention inserting it till nearly the end of the process. And now the 2 trim pots. Interestingly enough, the kit instructions say there should be a 5K ohm pot here, but the part is marked 10K. They didn't make any allowance for the part substitution in the instructions. And now all the capacitors. And the 2 LEDs. Should be noted here that even though it says watch polarity on the red LEDs, it does nothing to tell you how to watch the polarity, and it restates it, watch orientation on the parts list, but it doesn't say anything in the instructions about how to watch the polarity. The silk screen is marked with flats, but the LEDs as supplied do not have flats on them. Another common method is to use the shorter lead as the cathode, which would be oriented with the flat. And these LEDs were supplied with equal length leads. So kind of confusing as a beginner's kit, I would say. There was just the slightest little dimple on the cathode side, which looks a lot just like a molding error. It doesn't look big enough to be deliberate. But since they both had it, I thought, well, maybe that's supposed to be the flat. These are also exceptionally dim LEDs. I put the normal 10 milliamps through them, and they didn't light up very brightly at all. So ultra cheap or some weird thing, or I don't know what, but I guess if they do the job. Still, I thought an extra sentence in the instructions would have been good to instruct young kit builders or whoever how to tell one end of the LED from the other. This little 5-pin header is supplied, but the board doesn't have a place for a 5-pin header. It has 2 plugs, or 2 pins for VCC, and 2 for ground, and 1 for out. I'm not sure why there's 2 for VCC and 2 for ground. There's also VCC, ground, and out over here, which I didn't trace out the foils. I suppose they might all go to the same place. Kind of looks like they probably do. But it's not explained in the manual, at least at this stage. And it doesn't say that you're supposed to cut this apart, because there's no place on the board that it would fit the way it is. Now 3 pins of it do. I think if you cut them apart, hopefully they fit the board spacing. I didn't even try that yet, but probably they do. It looks like they will. So I think they should have said a bit more about that, either at this stage or earlier in the instructions. Okay, I put in 3 of the pins over here on the left, which has VCC, ground, and out. I elected to put 1 pin each in the dual holes for VCC and ground, just in case it's more convenient to apply power separately and then just use the output pin over here. But I could also run a single cable that does everything. The other holes for VCC and ground and the 1 hole for out here could be used to solder wires into and still leave the pins. So I think this is a fairly rational way of compromising what's supplied and what the board layout is. Be nice if the instructions said anything at all about that. And I've installed the IC in its socket. I skipped over the entire page and a half of pre-power testing and so on. It was all extremely rudimentary stuff. And really for the rankest beginner. It's kind of surprising that a brand name op-amp is used here. It isn't really identified as a 1458, even though the instructions call it a 1458. It's a TL082. Well, that TL082 is not the same as a 1458. I thought it might be Texas Instruments' own part number for the same thing, but it isn't. They are very different op-amps, although in a simple low specification circuit like this they're interchangeable, but the TL082 has got better specifications. It's a more modern design. 1458 is really just a dual 741, which also would be fine for this circuit, and that's what the parts list says. But again, it's kind of odd they didn't update their manual with the part they're actually supplying. And then over here it says it's a TL072 in the schematic, so that's a third place where they're at odds with each other. Although the bill of material or parts list does mention the TL072 and the TL082, or the XR082, but then way up at the beginning it says it uses a 1458. So again, just lack of attention to detail in preparing the manual, which again is not a problem for an experienced person, but since this kit is targeted at beginners, that kind of thing could really be confusing to them. Okay, I'm ready to do my tests. I've got my scope set up here, Okay, I'm turning the power on, 9 volts, and as expected I get a flat-topped waveform, but at least it's oscillating. And now I'm supposed to adjust this other trim pot, which my screwdriver is too big for, to get the cleanest output waveform. Still a little bit goofy at the bottom. There we go. If I go more, then it starts getting a little lopsided. So I want to go until it just starts rounding off there. Now, right now I've got a frequency of, what do I have? About 2.3 divisions, and I'm at 1 or 0.5 milliseconds per division, so 0.5 milliseconds times 2.3 divisions is roughly, okay, that, and then take the reciprocal of it, so it's about 869 hertz right now. I want to get it down to the point where it's 2 divisions, so I should be able to adjust the other trim pot here. It says to have it in the middle of its rotation to start with. So let's see here. Oh, that's amplitude. It's not substantially changing the, well, it isn't changing the frequency at all. It's at that frequency. So it's a little bit off. I think it's supposed to be 1 kilohertz by default. I don't know if it said it anywhere except on the listing. It just says it's an audio oscillator. I don't think it mentions what frequency you're supposed to get in the instructions. At least not up to this point. But at least it's in the ballpark. Well, I turned the page in the instructions. It tells you how to check for optimum results if you don't have an oscilloscope, just based on DC voltages. And you know, I've optimized the waveform as much as I can, but then you turn the page and you think it'll tell you something about how to adjust the other pot, and all it says is have it in the middle of its rotation, which is kind of odd. And this is a 10K pot instead of the 5K it's supposed to be. So maybe it should be more like this. If I go in the other direction, it starts getting flat bottomed. If I go way over to this side, it's a lower amplitude, roughly for pushing 5 volts peak to peak. What if I change my power supply to 6 volts? Well, now I'm down here. It may not be possible to make this produce a clean wave. No, it just cannot function as a sine wave generator at 6 volts. That's disappointing, because I was hoping I could run it at 6 volts. Alright, we're back to here. Have to adjust the trim pot again. Try to get that. The waveform starts getting more squirrely as I reduce the amplitude. It really is closer to a good sine wave just here before the peak on the bottom starts flattening out. And then adjusting the other trim pot I can reduce. It seems like it's kind of an amplitude adjust, but barely. Not really clear what the function of it is, except to dial in for best results. And that's probably about here. So let's find out what frequency we actually have here. I want to make sure I know what it is. No way on here with the pots to adjust the frequency. And I thought that the listing said there were pots on here to adjust amplitude and frequency, and that's not the case. Disappointed. I think it should be better than that. Let's take a look at the frequency we're getting out of this. I was messing around before and not really being careful at what I was doing. So I'm verifying that I'm on 0.5 milliseconds per division, or 500 microseconds per division. I've positioned it horizontally so I get the top of the waveform here, and it's 1, 2, 3, 4.5 divisions over. So I can go 500 times 10 to the minus 6th times 4.5 divisions gives me 0.00225 milliseconds, and then I take the reciprocal, and it's 444 hertz. And just for yucks, not that I expect there to be any difference, I'll hook up my DSO. And we're getting 500 microseconds per division, 1, 2, 3, 4.5 divisions, and it's reading out 442 hertz and change. So I wouldn't have expected there to be any difference, but just in case one of the other's time base was off, at least they're agreeing with each other. And we're getting, what do I have here? Vertical 2 volts per division, so 1, 2.5, close to 3 volts. I'm sorry, 3 divisions at 2 volts per division, right? Is that what I'm at? Yeah. So, 6 volts thereabouts. I wish it was adjustable, both in frequency and in amplitude, with the pots on the board. Now let's do a little bit of calculation here just for fun. The formula for a Weenbridge or Veenbridge oscillator is assuming the two RC networks have the same resistor and capacitor values. And I haven't done one of these in a long time, but I seem to remember it was 1 over 2 pi RC, where R is the value of either of the resistors and C is the value of either of the capacitors. And I dug back and found that they did mention that same formula in the circuit description, so my memory's not totally shot. And where R is 68K approximately, 68K, and then whatever you dial in with the trim pot for best results, and C is 0.005 microfarads, both these places, it calculates up to 468 hertz. So we're in the ballpark. Component tolerances and so on make the difference between the reality 444 or 442 hertz measured and 468 hertz calculated. Just the Wikipedia page on the Veenbridge Oscillator, and it confirms that it's named after Max Carl Werner Wien, a German physicist and director of the Institute of Physics, blah blah blah, and as it is a German name, it should be Wien, so that's the pronunciation. And once again, it mentions here that assuming the resistors and capacitors on both of the two filter circuits. It should be 1 over 2 pi RC. And once again, it shows the same thing, that you've got an op amp with negative feedback through a resistance, and then another resistance element to ground. And one of those, either this one or this one, in this situation it's this one, is something that's there to stabilize the oscillation, and it's an automatic gain control. And you've got this RC parallel and this RC series, and again, normally the two R's would be the same value and the two C's would be the same value, and then you have that simple formula. So actually, it's a nice article in here, and I've built these before. I used to build audio equipment for recording studios and radio stations a long time ago, and I often included a 1 kilohertz sine wave oscillator based on the Veenbridge Oscillator circuit using an op amp, and I actually used back-to-back diodes as my stabilization component, but in this kit it's using back-to-back LEDs. Similar result. And these things go way back, you know, they had them in the vacuum tube era and so on. As it says here, the key to the Veenbridge oscillator's low distortion oscillation is an amplitude stabilization method that does not use clipping. Instead of using a lamp in a bridge configuration for amplitude stabilization was published. The idea of using a lamp in a bridge configuration for amplitude stabilization was published by Meacham. Hewlett used an incandescent bulb for this purpose. Light bulbs have their disadvantages when used as gain elements in Veenbridge oscillators, most notably a very high sensitivity to vibration due to the bulb's microphonic noise or nature. And as the article goes on, after my phone call interruption, modern Veenbridge oscillators have used other non-linear elements such as diodes, thermistors, field effect transistors, or photocells for amplitude stabilization in place of the light bulbs. Okay, I reran the calculations assuming a 33K resistor instead of a 68K resistor in those two places. And it calculated out to 964 hertz. Slapping it on the DSO here, it's coming out as 937 hertz. So in the ballpark, much closer to the 1 kilohertz I wanted. Probably not worth tweaking beyond this point. Giving me, what am I at here? 1 volt per division, 2 volts per division. It's giving me 1, 2, 3, 4, 5 volts peak to peak, which is quite different from the 2 volts peak to peak that it says in the listing. It's not a bad amplitude, but it's a bit more than I really wanted. Probably still be adequate. So here's how the Veenbridge oscillator is laid out in this kit. Because it's a bipolar output, in other words, it can go, actually it's an alternating polarity signal, or true AC, as opposed to a modulating DC signal. It does go above and below ground or circuit common, but it uses a single pole or monopolar supply, which is called VCC and ground. Supposed to be 9 volts between those. So we have to establish the artificial ground for the circuit common, and that's done with two 10K resistors and a voltage divider between VCC and ground. So we actually get 4.5 volts at this point. Now we have the classic circuit with an op-amp having negative feedback. This is enhanced a little bit by having this 220K resistor in the negative feedback loop, paralleling the 2.2K resistor and the two back-to-back LEDs, which provide the automatic voltage compensation or stabilization circuit. So that provides two feedback paths, and then part of potentiometer R4, which is a very low value part, only 500 ohms, and that goes to the virtual ground. And then there's a 100K resistor from the wiper of that to here. So that gets you your negative feedback with the compensation. Now, from the output as far as positive feedback, we have a 68K, and again in my circuit it's not 68K, it's 33K. So I fixed my schematic to say 33K. That's the way I built it. And then the 5 nanofarad capacitors. So this is series RC, this is a parallel RC, and then we can tweak the resistance a little bit with this 10K potentiometer, which we're using only as a rheostat. So we're only using one side of the element and the wiper. And then the bottom of this goes back to the virtual ground. And so this is actually oscillating all above, or up above and below the 4.5 volt level. So it's not alternating above and below ground or 0 volts. So we need to get that down to ground level, so this DC blocking capacitor is here on the output. So it strips out that 4.5 volt offset and leaves you with a sine wave which goes equally above and below ground. I decided to read through the more detailed theory of operation, but it says real world engineering, variable gain control. And he talks about how even though the Veenbridge Oscillator is a very old circuit, and then he mentions that William Hewlett at Stanford University, who eventually helped form Hewlett-Packard in 1939, did it with vacuum tubes, and that for the automatic gain control necessary for the right oscillation, you need to have a feedback element that its resistance changes or inversely to the amplitude of the output. So he's like, well, Hewlett used a light bulb, you know, and well, we don't want to burn anybody's fingers, but you know, those light bulbs didn't get hot. At least not in op-amp or transistor-based Veenbridge oscillators. You know, they get slightly warm. They don't really need to incandesce, so that's sort of disingenuous here, either deliberately or accidentally. So he says, we ask ourselves, what's the modern high-tech equivalent of a light bulb? This whole paragraph just doesn't ring true. I hope that the guy didn't really come about it in this way. I mean, it's a classic circuit. You can look in any textbook or data book and find all sorts of examples of exactly what he's got here. I don't think he discovered it for himself, but maybe. And then he makes a joke down here, says, if you become a fan of the Veenbridge Oscillator, does that mean that you're a wiener? Ha 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 ha. I don't know. And here's the other oscillator. This one is purchased from Amazon. Before, I couldn't remember which kit came from eBay, which one came from Amazon. But I'm confirming here that the signal generator kit, as opposed to just the simple oscillator kit, is sold through Amazon. And it's, well, they don't say here what it costs, but I can go directly to the listing, and it's $13.99. Signal Generator Do-It-Yourself Kit KKMoon. Here are all the parts. It does come with a printed manual, although it's really just one side of a sheet of paper. And it's some really weird low quality paper, like it's 10 times recycled or something, but it'll work. Parts for the case. It's a plastic case, laser cut, 3 knobs, some hardware, the one and only IC and its socket, a couple of pin headers, 3 potentiometers, the power connector, a terminal block, 2 shunts, 5 fixed resistors, 3 electrolytic capacitors, and 5 ceramic capacitors, and the circuit board. Fiberglass, double-sided, silk screened. Looks pretty good quality. Well, this is a bit more of a basic kit in that it doesn't offer a lot of instruction, but should be adequate. It does have a parts layout, the bill of material, more parts list, continued over here. Instructions using some weird typography. The welding installation considerations. Follow these steps. The components are welding the front board from low to high principles, namely the first low welding components, such as, lots of commas in here, capacitor, resistor, diode, etc., welding IC socket, terminal blocks, finally the power socket, adjustable potentiometer, the back with diagonal cutting pliers to cut the short pins as far as possible. So yeah, kind of Chinglish, but should be adequate. I'm starting out with the IC socket, the fixed resistors, and all the capacitors. And the 2 pin headers. The barrel connector and the 3 position terminal block, which is for sine and triangle wave outputs on the left, square wave in the middle, and ground on the right. And the 3 potentiometers. Important to note that the left 2 ones are 50K pots and the right one is a 100K pot. It doesn't exactly stress that, but they are called out by those values. This barrel connector is for the power supply, which is not included. It needs to be between 9 and 12 volts, and they say if you put more than 12 volts on it, the output waveform becomes unstable, so probably 9 volts is the best. And it's a now pretty ubiquitous 5.5 millimeter by 2.1 millimeter center positive barrel connector. There used to be tons of variations on this, but it seems like the electronics world has more or less standardized on this size, and it's the only size I stock in my parts bin, so luckily it's the same, or conveniently it's the same size as what the kit requires. So there's this little green shunt which can go either in the triangle or the sine position, and this other one that can have 5 positions, which selects 5 different capacitors, and it can be in one of those positions. It's not entirely clear to me why you can't have the waveform be simultaneously available on the sine and the square wave outputs. but it says you can only insert it in one of them. Maybe that's because there's only one shunt provided. I don't know. But the fact that there's a selection there does suggest to me that, yeah, I don't know. There is a waveform select couple of pins on the IC, and it looks like from the schematic that when the jumper is in the sine wave position, it's shorting those two, and when it's in the other position, it's doing nothing. So that may just be a storage position when it's in the square triangle wave or sine triangle wave. Oh, I see. Yeah, it's one output that can be sine or triangle, and then you pick with this jumper whether it's going to be one or the other, and then you always have the square wave. Apparently that's how it works. And then I think you can select your frequency range here, and this is amplitude, and this is coarse and fine. Presumably that's coarse and fine frequency, not coarse and fine amplitude. That wouldn't make sense. So I've got my scope hooked up, and I'm going to turn on power. It's set to 9 volts. So I have a square wave there. And adjusting the coarse potentiometer, I can move it around a bit from about 90 kilohertz to 60 kilohertz. 90 kilohertz when it's clockwise. And then I can make, well, I would call that coarse. Oh, it is. Coarse is the right-hand potentiometer. So yeah, that goes from 90 kilohertz at the counterclockwise end up to 1.2 megahertz. I just enjoy letting the scope figure out how to adjust itself. Not a very precise waveform. It starts squaring up. When it gets down around 90 kilohertz. And what are we here? We're at 2 volts per division. And I can adjust the amplitude. Well, that doesn't do a damn thing. Maybe the amplitude only works on the sine wave output. It's not changing it hardly at all with the square wave. Sine triangle. Well, that's not a very good looking sine wave, is it? Oh, jeez. Okay, it's maxing out. So once again, I gotta figure out what my vertical is set to. I so rarely use this scope, I forget how to use it. I don't see where it's telling me on the screen what my vertical is. Oh, that's 2 volts there, so I guess, yeah, that's where it says. There's quite a lot of offset there. The output seems to be riding on a DC level, which is not good. So right now I've got the same waveform on both scopes, and I'm at 1 volt per division here, so it's about 4 volts peak to peak. And if I go to ground, it's off the picture. If I move ground here and go to DC, it's way up there. So it has a big DC offset. And again, we're at 213 kilohertz. What happens if I move this jumper? Yeah, it changed the range dramatically. I'm at only about 11 kilohertz here now. I'll move it again. Goes down to about 600 hertz. It's getting to be kind of pointy. It's almost more like a triangle wave. And if I move the jumper again, we're down to about 27 hertz. And finally down here, it's really, too slow to discern the waveform. It's less than 10 hertz. So I want to be up around 1 kilohertz. Let's go back here. So I'm still kind of in the 2 volt peak to peak range. And the amplitude changes contrary to the pot. That's really bad. You turn the pot clockwise and the amplitude gets less. Okay, so I'm trying to dial it in at 1 kilohertz here. I've got the course set pretty close. But it's too touchy to move it in very tightly, so I'm going to use the fine. There, I'm at 1 kilohertz. I wouldn't call that a very great sine wave. That's pretty far from being a sine wave, actually. It's just a triangle wave with a bit of filtering. What happens if I move the jumper and say it's actually supposed to be a triangle wave? Well, then you get one at a different voltage. What happens if I go to a lower voltage here? I'm going down to 6 volts. The waveform is just garbage. It doesn't even know what it's doing. If I go up in voltage to 7 volts, it starts approximating the waveform, but it has that real sharp glitch in it. If I go to 8 volts, it starts looking like it should. If I go to 9 volts, then it's better. Does it get any better if I go up towards 12 volts? No, waveform does not improve. So it's perfectly good at 9 volts as far as perfect can be considered with this thing. This thing's kind of a piece of crap, actually. I'm kind of very disappointed in it. I'm not sure what they did wrong with this design, because I thought this IC could do a better job of that. That's not a sine wave. That's a messed with triangular wave. Go back looking at this thing here. It says high precision function signal generator. Well, that's very far from being high precision, if precision means the waveform. It says the sine wave distortion is less than 1%. That can't be true. Zero to 3 volts at 9 volts. Well, that isn't true either. these specs are pretty specious. Is a professional product? I don't think so. I think the whole reason that the amplitude pot works backwards is because somebody screwed up on the circuit board. I don't know if it's showing up there. There's a tiny little jumper right there in the middle. There's a jumper between the center and one side of the pot, and moving that jumper to the other side should change that so it works correctly. In the schematic, the pot is just a resistor between this voltage divider here. Right, so this generator, the XR2206CP, should be able to work with either a bipolar supply or the unipolar supply like this, with just a single power supply. But if you do that, then you need to connect the amplitude adjustment resistor, which comes out of the MO pin. It's a adjustable resistor here to the ground reference, which should be halfway between VCC and the negative supply. But when it's a unipolar supply, you need to create a point halfway between VCC and ground, which is done with these two 5.5K resistors, and then the amplitude potentiometer coming off of that middle point and going in. So what's actually there is this resistor is already there, and currently they have it set so the wiper is connected to here. So when you adjust the wiper in this direction, you're increasing the resistance from here to here. Now if you leave everything alone and move the wiper to that side, now when you turn it in the clockwise direction, it's progressively shorting out more and more of the resistor, so you just have the little resistor here, so it actually decreases the resistance as you move it clockwise. So that's the only thing that really should need to be adjusted on this, and it's pretty clear from the circuit board foils that the wiper of the pot does come off the middle. So let's see, the wiper's correct. We just need to also connect the wiper to one end or the other of the element. The problem here comes because they didn't follow best practices when they laid out the circuit board. Best practice would indicate when you're using a potentiometer as a rheostat, that or just a simple variable resistor instead of as a voltage divider, that you connect the wiper to one end or the other of the element instead of leaving one end of the element hanging. It's not ideal to leave one element hanging. And if you did that, then all you'd have to do is move the jumper or whatever foil or jumper there is from the wiper to one end or the other of the element, and you'd be good. Now what they've actually done here, here's a top view of the pot. It's 3 terminals. There's the foil that goes to IC3 or the IC pin 3. Then there's a jumper on the back side of the board to here. This isn't connected anywhere else on the board with a foil. Then this side goes to the 2 voltage divider resistors that are at 4.5 volts, assuming a 9 volt supply. So since it's reading the wrong way, what we really want to do is get this over to here and put the jumper here. you know, you definitely need to move this jumper to this side. So you basically are going to have to cut this and cut this, then jumper this point around to here, and put a new jumper in here. Pain in the butt. Okay, so what I did here was I cut a foil, a tiny foil between these two pads on the circuit board, and then I cut the foil that goes underneath the R2 silk screen coming off the upper left hand corner of the amplitude pot and going under these resistors. I just cut it right here before it goes under R3, and then I put in 2 new jumpers just using wire wrap wire. I just stuck them into the holes alongside the potentiometer pins for these two. That replaces the circuit board foil jumper that used to go here and here. Now it goes from here to here. And then I connected this pin to this pad here. It could also be this pad, but I put it on this one. These two are connected on the other side of the board. Or maybe it's this side. It's actually on this side of the board. So that replaces the foil we cut that goes from this pin down to here on the other side of the board. So that should get the amplitude pot working in the correct direction. Now I read the XR data sheet, and they don't actually address the floating output, or not floating output, they don't address the DC offset of the output with the sine waves. But they also had a circuit board that they put out that was used for people to evaluate the IC, and that one had a 0.1 microfarad capacitor coming off of pin 2, which is the sine wave output. It's also the triangle, sine triangle output, which is STO, sine triangle output. So you obviously need to do that, otherwise your output is going to be floating at some voltage that you don't want it to be. Now, if you had this running off of a bipolar power supply, then the output would be centered around ground, and you wouldn't have to worry about that. But with a unipolar supply, it's going to float, you know, somewhere around 4.5 volts if you're using a 9-volt supply. And again, I'm using float incorrectly. It's going to be offset from ground by about half of your power supply voltage, which is something you don't want. So really, if you're going to put this in something where you're going to use it, you need to put a little 0.1 microfarad capacitor. This is a axial lead one, but a normal radial disc capacitor of 0.1 microfarads would work too. They strongly recommend having a filter capacitor from IC pin 3, which again is the wiper of the amplitude pot. They strongly recommend having a capacitor from that point going to circuit ground, and it should be approximately 1 microfarad. So either a 1 microfarad disc capacitor or a 1 microfarad electrolytic. And I think I'm going to put it on there. It's probably not strictly necessary, but it's something they recommend as being part of the basic circuit. And I don't think they would recommend it as part of the basic circuit unless it was a good idea to have it. So I'm going to see if I can figure out how to best do that. Okay, the other thing the data sheets recommend is a sine wave symmetry and shaping adjust potentiometer of 25 kiloohms or 25K wired between pins 15 and 16 of the IC. with the wiper connected to ground. This is optional, but it's supposed to be used for optimum sine wave shape. So I dug through my junk box and found this old 25K trim pot, which I've temporarily wired up to pins 13 and 14, and the wiper jumpered over to ground. And I'm going to try out this circuit now with my modifications. I'm also going to put this 0.1 microfarad capacitor on the output for the sine wave output here. Well, all this is turning into a bust. That capacitor, the 1 microfarad capacitor on pin 3, just seemed to totally hose the circuit. I don't understand why, but it doesn't generate any waveform when that capacitor is there, so I took it back out, got the waveform back. Now I've got that trim potentiometer in there for symmetry, and it just does all sorts of weird junk. But it's still a sucky sine wave. Has a lot of harmonics in it that it shouldn't have. And it should be better than that. It really should be. I've read online that there's quite a lot of these chips that are counterfeit and not really what they should be. Since this is a Chinese kit, I suppose it's possible. I'm kind of inclined to try placing an order for a brand name XR2206. Plug it in here and just see if it makes any difference. Because it doesn't seem like it's really working quite right. Yeah, I'm getting a waveform and so on, but I don't like that aspect of it at all. Alright, I realized that I needed to fix this one resistor R1 over here. That was a 1K. It should be a 10K according to the data sheet, and it's really too low of a value considering that the output voltage is going to be, the square wave output voltage is going to be considerably higher than any normal logic level you're likely to use. So putting the 10K in there pulls it up just as well for any logic family, TTL, CMOS, whatever you're going to run into. But at the same time, you know, if you're running into, say, a 5-volt CMOS or TTL circuit, it's not going to be bombarding those ICs that are running at 5 volts with a 9-volt square wave, which is what we've got here. It's just better with the 10K, so I've changed that part out. And I'm using a 0.1 microfarad coupling capacitor coming out of the sine wave, triangle wave output. So now I've got 0 volts there, and the output is centered plus and minus around it. We still have this really pointy pseudo sine wave, and I'm blaming that to some degree, possibly, even though the XR2206 never had a really good sine wave. It may be a little better using a more legitimate IC than this who knows what brand possible rip-off IC. So I've ordered from Janeco here a couple of presumably legitimate XR, that's the original brand, ICs. Now with a lot of rebranding in China, you don't really know just because they put an XR logo on there if it's really XR. Alright, so I'm going to substitute that in here and see if there's any noticeable improvement in the quality of the sine waves. Okay, that XR part's in here now, and let's turn the power back on and see what we get. Well, it's not really that much better. There might be a little more curvature here, but yeah, it's still a pretty poor substitute for a sine wave. Now let me check the voltage here right at the moment. What am I looking at here? Is my probe on? It's on times 10. So I'm on 1 volt per division. So it's close to 3 volts peak to peak. Let me turn the amplitude down a little bit. So it's closer to 2 volt peak to peak. Yeah, it's still a poor substitute for a sine wave. I'm right at 1 kilohertz here, and showing that 1, 2, 3, 4, 5 divisions at 0.2 microseconds or milliseconds per division. I am at 1 kilohertz, and I also put this capacitor back in here. I had it incorrectly connected before. I had it connected to the wiper of the amplitude pot, in other words the pin that goes directly into the IC, and that was just because of the weird way the schematic was drawn originally. It needed to be at the center of that voltage divider instead. Now again, that's probably not strictly needed, but since the datasheet unequivocally recommends it, I put it in there, and now it's not messing with the operation as it did before. It's just a matter of getting it connected to the right side of the potentiometer. Now that I have the presumably legitimate XR chip in there, I reconnected the Symmetry potentiometer to the circuit. So I'm going to see if that works now. It definitely freaked out the other chip. Okay, power back on, and I'm getting a triangle wave now instead of a sine wave. But again, I don't know if I've got this pot adjusted anywhere near correctly. This might not be intended to be used with the sine wave output. So let me try moving the jumper here to the triangle wave position and see what this pot does now. Well, nothing good, that's for sure. It's kind of just crap. So that's not helping at all. Alright, moving it back to the sine wave position. That's just about as good as it's going to get. Nothing else to be done about it. However, now that I've got this presumably XR chip in there, the old one would bonk if you went above 12 volt supply voltage. So I'm going to crank up here. Go up in voltage a little bit. That's 10 volts, 11 volts, 12 volts, 13, 14, 15, 16, 17, 18, 19. Still getting a perfectly good waveform out of it. The old one definitely didn't do that. If you went above 12 volts, even just a fraction of a volt above 12 volts, it was getting all squirrely. And this one will go down around 7 volts. The output starts getting pretty weird. At 8 volts it's okay. 9 volts. So this definitely works just as well at 9 volts as it does at, say, 12 volts. And unlike the chip that came with the kit, this brandless XR2206. This one does appear to be a more legitimate part, and it's working over the voltage, the power supply voltage range that it's specified to work at. So they're definitely putting a kind of a crap chip in this kit, at least with the one I got. And from a little research I've done online, apparently it's pretty common that they get this rip-off chip that's not the same internally in probably more ways than one to the legitimate one. So if you build this kit, you might want to consider going out to a legitimate electronics supplier. I got this one from Jameco Electronics. A lot of other places don't carry it anymore since it's such an old chip. But Jameco still sells a kit based on it. They have their own version of this, it's just bigger. And maybe for that reason alone they still sell this chip. Again, I don't know if it's really an XR chip, but it appears to be legitimate in its internal functionality. I was saying before how I changed out R1 here with a 10K from the original kit's 1K pull-up resistor. And that's because what's really happening in here, and see if I can sketch it out a little bit on the back of the manual. What's really inside the chip, here's the side of the IC, and inside of it's an NPN transistor that's connected to a couple pins on the IC. And this goes to circuit ground, and this goes through the, oh, I'm sorry, it doesn't go through the resistor. It goes to the square wave output terminal, and then there's this resistor going to VCC. And this should not be the 1K that's provided with the kit. It should be a 10K resistor according to the XR spec sheet. So the way this works is when this transistor is off, it's like an open circuit. It's an open collector, as they would call it. And the resistor pulls the square wave output pin up to whatever VCC is. In the case of my kit, I'm running it at 9 volts. So you get a square wave that's 9 volts at the top and 0 volts at the bottom. Now, a more flexible way of doing this would probably be to leave off this resistor entirely. Just don't even have R1 in on the circuit board. Just have the output of the IC going to the square wave output terminal. And then when you run that to your external logic circuit, you know, it's going into some gate or another. On that logic circuit, put a pull-up resistor. 10K is probably a good value. And then have that go to the VCC or V plus of that circuit. 5 volts, 3.3 volts, whatever it may be. Now the pull-up is controlled by the logic power supply circuit, not by whatever you're choosing to power the function generator from. I think that's really the best way to do this, but since I don't plan to use this for its square wave output, I'm going to leave that 10K resistor in here for the time being. I have an idea how I might use this for a particular application. In that case, it doesn't matter what the voltage of the square wave is. Okay, so I'm going to build the case now. This is included with the kit, and really it's probably half the value of the kit. So first thing I got to do is strip off the protective paper on the laser cut acrylic. There's also some quality control problems here. The laser cut or laser engraving, which is done on the back side, you can feel it on this side. is incredibly sloppy. It should be a lot nicer than this. You know, it doesn't look too horrible here, but some of these characters, especially over here, are so blurred out. You know, something wasn't working quite correctly there. I wonder, though, maybe it's not the laser cutting itself. Maybe there's some residual adhesive or something. I'll take a look at this through my magnifying glass. Alright, looking through my magnifying lamp's lens. I carefully picked away at the back side of these engravings with the tip of my X-Acto knife, and even though it's still sloppier than I've seen a lot of other laser engraving, it's definitely more legible now, having picked all those little tiny pieces of paper out that were stuck on the inside of zeros and in the crevices of ends and things like that. So that's worth doing if you build one of these. The instructions don't tell you how to assemble the case. There's the bottom, the front, the two sides, which are different. This one has a small squarish cutout in it, and this one has a longer cutout. That one goes on the right, and both times the cutout goes towards the top when you're looking at it this way. It doesn't seem like this bottom part has a top or a bottom. It could go either way. I think it's symmetrical. It's really just the side pieces that you need to worry about. I wasn't sure how I was supposed to use the hardware. What I ended up doing after some experimentation was putting these short screws, the 4 short screws, in from the bottom and having the nut on the top, and then sitting the circuit board down on top of that so it rests on the nuts, but nothing holds the circuit board down. Now there is an extra nut here, and I don't know if that's intentional or if it's just a spare, but I noticed that when I did it this way, the bottom of the power jack fits perfectly with the cutout, and likewise the bottom of the cutout fits perfectly with the terminal block over here. If you do it some other way, the board sits too low and you have to file away at these cutouts. Now, there are no side slots. Well, there are side slots, but there's only one on the bottom here and one on the bottom there, and that's because there's stuff too close to the top. Now if I set this down on here, yeah, so these tabs, that's this tab here and this tab here, go into these holes. It sits down there very nicely, and it clears this jack and clears this without any need for filing. And I think that's the way it's supposed to be. So now I'm going to take this back off, and I'm trying to decide. Yeah, I think it's okay to go ahead and tighten up these nuts here. I had them kind of loose, but I'm going to tighten those up now. With that done, I'm going to put in these side rails. Where's the other one? That's the problem with transparent parts. Okay, and I really should at least wipe off the inside of this so it doesn't have any big smudges on it. Shift it around until I can get it to align with the the tabs. It's always a little tricky with these things. Finally it drops in after a little messing around. And then the only thing that's left to do is put these bigger screws in. And I think they do need to go from the top. Oh, wait a second though. I forgot. I was going to put in this remaining nut on 1/4 of the board. Probably this one at the upper right. Since it's here, I can help hold the board down in this area where it's probably most important, right next to the terminal block. Just like that. And these screws need to go in from the top because the holes in the front panel are bigger than the holes in the back. And I think the idea is that these just form their own threads and screw into the bottom acrylic panel, making their own threads in there, sort of self-tapping. Okay, there's the finished product. Well, almost finished. I don't have the knobs on it yet. But yeah, the case went together pretty easily. It's a bit of a trick to figure out how tight to make these 4-corner screws. They go in pretty stiff because they're cutting their way into the plastic on the bottom. And it would be pretty easy to over crank them and probably break off the tabs or bust out the hole or something if you over tighten them. So I was just cranking down a little bit at a time and testing for looseness between the top and the bottom, just trying to, you know, wiggle them a little bit with my fingers until it felt like it was just tight but not tighter. And then I called it quits as far as tightening each screw that way. And there is an extra, at least in mine, there's an extra short screw. Absolutely no place I can see to put it. Like I said before, I just used the spare nut to put on one of the screws for the circuit board. It doesn't seem like it's going to go anywhere. It seems to be pinched in there plenty tight, just sitting with the screws going through the holes on the circuit board. I think it's because, for example, that electrolytic comes right up to the top panel. The IC almost does. This other small electrolytic here and this one are the same height. They didn't make this any taller than they needed to. That's probably a good cautionary thing. Make sure you push those electrolytics all the way down to the board. Otherwise the case will not come together on these side plates because they're just the same vertical dimension. Let me put those knobs on. Okay, there it is now. The holes in the front acrylic panel are big enough to encompass the bottom of the knobs, so you could push them down so they're a little bit inset. I did that, and you can see what happened here. For some reason, they didn't all want to go all the way down then, and I had trouble prying them back up. Sort of a bugger there, so they're not all the same height. I think you might want to just stop with them when they're more or less level with the top. And I chose to align the pointers with the slots on the top of the shafts of each potentiometer. And they all turn okay that way. And I just had to reset this since I want to use it as a 1 kilohertz 2 volt peak to peak oscillator. I had to hook it back up to the scope and get those knobs adjusted. I think I'm going to make a small Sharpie mark on the acrylic so I can get it set back to approximately the right levels. It's kind of unfortunate they didn't include a few pads for the bottom. I just had these laying around, 3/8 inch felt pads. Just makes it a little nicer on the table. Okay, just to sum up, after all the meandering in this video, it is after all a video of exploration and description. I just want to go over my final closing thoughts on these two kits. And you may ask what this thing is in the background. My beloved levitating globe that I have in my living room just spontaneously stopped working yesterday, actually. Just sitting there in the living room, and all of a sudden I hear a thunk, and the globe has dropped, and I thought maybe there was a power interruption. That's usually the only thing that causes it to drop, but nope, something was dead in the unit. It's all electronics, of course. There's some sort of little sensor. I presume it's a Hall effect sensor. There's a huge permanent magnet, like a big powerful speaker magnet, and then there's a couple of electromagnets in here, and then this sensor. There may be another sensor too, that's the only one I can see, and then a control board. And you could see it was trying to work, but it would only hold for about a second and then dump the globe. Something was failed on it, and I've decided not to repair it. Once I got it open and I saw, I don't know, it looked like something was corroding in here. I'm not sure what that is, but the new ones are so inexpensive I decided not to mess with it. Anyway, back to the subject at hand. We'll try to ignore that elephant in the room there. So this one from Rainbowkits, it basically does what it's supposed to do, but there are some issues with the documentation. Normally, this is supposed, this is plugged as being a signal injector for tracing signals through amplifiers and so on. That seems to be its primary purpose, and to be an educational tool, just like a building block. But unless you're using it as a fixed frequency signal generator for signal injection type of applications, it's kind of useless as a function generator. It only does a sine wave. It has very restrictive voltage ranges, and it's not adjustable with any potentiometers. You really just set it up for whatever frequency it happens to generate, given the component tolerances. It's not the standard 1 kilohertz unless you change resistor values. It's, not even 500 hertz, so it's a much lower frequency than you'd usually want. I don't know, some odd decisions are made here. Still, it's not like it's bad quality or anything. There were some things I wouldn't have done, like this is a dual op amp, and the other half, the other op amp in the package isn't terminated in any way, it's just left floating. It's not the end of the world, but I would say that good practice is to do something with those inputs. It's not the end of the world. It doesn't overheat or anything, but still. It seems like there's a disconnect between the documentation and the parts provided. The LEDs, as I already said, at least on this particular kit, they may be using grab bag parts to populate the parts bags, but when you get an LED pair that has no easily discernible orientation marks, and both leads are trimmed to the same length, and you're selling this primarily to beginners, the instructions need to do more, and they need to be more careful with what parts they put in the bag. There are holes on the circuit board which have nothing going in them. The included 5-pin header is not described. It doesn't tell you that you're supposed to cut it apart to go in the holes. It doesn't recommend which holes to use. Really, for what these things cost, they should at least have included enough pins for every hole if somebody wanted to put them in there, and they should have described it in the instructions. And as I already outlined, the manual, while I give kudos to them for producing a printed manual with the kit, that's a big plus. It really needs somebody to go over it with a sharp editor's eye and clean it up, fix the mistakes, the inconsistencies, some of the silliness. Anyway, so it is what it is. sort of useful, but it didn't do anything for me, and I couldn't use it in the intended way that I wanted to use it. Now for the KKMoon kit, which is upside down. I've built other KKMoon things, and generally they're okay kits. In this instance, the manual was not as good as I've seen from them in the past. It does some weird things like in the parameters column, it just lists the actual printing on the part, which is cryptic. That's not a parameter, that's a part marking, and it's intermixed with the parameters, so that's kind of a mess. There is no description on how to build it for a beginner, so you have to know something already, probably to do this successfully. Again, at the low price point, you don't expect miracles, but I think they could have done a little better. And this is being sold by places in the States. You think that they might have looked at this product and said, you know, these instructions leave a lot to be desired. Why don't we type up our own addendum and stick it in the package when we sell these things? Or at least refer them to a page on our website that has some extra pointers or something. That was not the case here. The original KKMoon designers did not do everything they probably should have done to make this useful out of the box. It required some fiddling. For example, if you're planning to use this as a standalone function generator, which is, it says it's a function generator, it's not a building block like this other thing. It's a standalone device, and a standalone device with amplitude adjustment that does not include DC offset adjustment when there is a huge DC offset is, to me, kind of inexcusable. It renders it useless, especially to beginners who aren't going to understand the problems of the DC offset. You know, every real function generator has a DC offset, and it would have been easy enough for them to put it on here at minimal cost. Anyhow, so that's my main beef with it. And of course, the real failing here is that they've used some sort of a counterfeit IC instead of a XR2206 that actually meets the published specifications. It does not perform as it should, even though it works at some level. I have a feeling that the kit makers know about this because they mentioned that you're not supposed to use more than 12 volts. So they must have determined that this chip malfunctions even slightly above 12 volts power supply. And that's really bad. I think they knew about the inadequacies of this and still put the kit out. Some of these other things like stabilization capacitors, yeah, they could have left those off. They're recommended by the datasheet, but obviously it works without them. I think they really screwed up with the pull-up resistor on the square wave. They should have put that decoupling capacitor on the board instead of requiring the kit builder to have one of their own. They did make a definite screw up on the circuit board for the amplitude pot so that it works backwards. That's just a flat out mistake. The other thing I noticed is that the holes on the circuit board are huge, way bigger than they should be for the component leads. That makes it more difficult to solder. Even though I'm a very skilled and experienced solderer, I had trouble getting some of these to solder properly just because there was so much space to fill with the solder. And you could easily overheat some pins if you are a less skilled person in trying to do this. I think they probably should have included the little feet. Those are dirt cheap, cost an extra 3 cents, and keep you from scratching up your table. I think they should have included something else for the power supply, like the mating power adapter, if not a cable. but since this will run on 9 volts, including a barrel connector and a 9-volt battery connector like this in the kit, would have been something they could have done, and the cost would have been negligible. Even though this packaging is nice, I think it would have been nice if there would be something to facilitate wiring up a selector switch to this, so that you could do that instead of having to move this shunt jumper every time you're changing ranges. I know that would increase the cost more, so that would probably never happen. I think those are the main issues. This does work, and this guy is going to go and accompany my old 1940s impedance bridge that I'm doing a separate video on. It's going to replace the non-functional 1 kilohertz Hummer so that it can be demonstrated without having to lug around a full-size function generator just to demonstrate the thing or to play with it. It does work just fine for that, and it doesn't actually even need the capacitor, because the bridge kind of functions even with the high DC offset. But I did do most of my testing and demoing so far using the downstream side of the decoupling capacitor. So even though these are not really apples and apples, this is okay. I think they could improve it substantially with fixed up documentation and a couple of more parts provided, but it's very limited in what you can actually use it for. This is potentially more useful, but somebody buying it thinking it's going to have the functionality and utility of a proper function generator is probably going to be disappointed. Still, somebody who knows what they're doing and doesn't have overly high expectations of it, it's not a bad package.